guys, what's the crack? So in this video, we're going to go over the defects of vision. So this video is really helpful for you if you're studying medical physics as part of your AQA syllabus, which means that'll be on your paper 3 section B paper. And it's also helpful if you're doing OCRA, because OCRA needs to know quite a bit of medical. So remember if you're doing OCRA to check out your syllabus to see what exactly you need to know. But again, if you're doing AQA medical, you need to know everything on the slide. If you want extra help and extra information, remember always check out my resources. So literally just Google MyEd Space and then check out my resources for physics. We have loads of A-level notes there for you. So completely free. So defects of vision. Okay, so in the last video, we went over the whole thing about the eye. So here's our eye again. So we know we've got our lens, which is attached by our suspensory ligaments to our ciliary muscles. Now we know when it's all relaxed, we said in that last video, we can see things that are far away as infinity. So infinity just means like super far away, and light from things that are really far away comes in parallel. So we can see things from infinity up to about 5 meters away from the eye, okay? But if I want to see anything closer than 5 meters, so if I want to see something that's 1 meter away or 50 centimeters away, what I need is to get a more powerful lens. So the power of a lens is equal to 1 over its focal point, okay? So what is the focal point? So this lens inside your eye is called a convex lens. So a convex lens is a converging lens. So what that means is if I've got my convex lens that's fatter in the middle, but sometimes I want to draw the lens. So to show something's fatter in the middle, you can do these things with the arrows. See how the arrows kind of try to show you that it's fatter in the middle. Now a dotted line across the middle, that is called your principal axis. Okay, so what a converging lens does is if we have parallel rays of light, so rays parallel to that principal axis, it will refract them. So remember, refraction is the change in direction of light when it enters different optical densities. So again, we're going from air and we're going into that cornea we're going through the cornea into that lens in our eye. So what's going to do, refract them and cause them to pass through that thing called the focal point. So that is my focal point there. So the focal point is the distance between when those parallel rays of light, those rays parallel to the principal axis, where they converge through. So the focal point is the distance then from the lens to that focal point. So that's there, what we call the focal length or the focal point. So that tells us about the power of a lens. It's 1 over the focal length. So if the focal length is much closer to the lens, we know it's more powerful. If the focal length is much further away from the lens, it's a less powerful lens. So like we said, if I have laser light from something that's much closer, okay, so let's say we're again 1 meter away or 50 centimeters away, those rays of light, they're coming in at an angle, right? Because light diverges, it spreads out. So I need a more powerful lens because I obviously need to refract them by a lot more in order to get them to converge onto that point at the back of the eye. So we want light rays to be converged onto the back of the eye, the fovea. So again, just a reminder from that last video, most refraction happens at the cornea, and then the rest of the refraction happens at the lens to focus those light rays on the fovea. So again, I want them all to get focused on the fovea. So if I want to see anything closer, I need to get a fatter lens. To get a fatter lens, our ciliary muscles are going to contract. So again, C for ciliary muscles, C for contract. So our ciliary muscles are going to contract. It's going to make this lens then a lot fatter, so more powerful lens, a lot fatter, and that's why then I can see things much closer. And I can see things up to about 25 centimeters away from my eye. I can focus on them about 25 centimeters away. And that is called the near point of a healthy eye. That's the closest you can see from a healthy eye. And again, for a healthy eye, the far point, the furthest you can see is that infinity, so super far away. Okay, so defects of vision means something's not going right. So the first one I'm going to focus on is myopia. So myopia is someone that is short-sighted. So short-sighted. So what that means is they can see things that are really close to them, right? That means they can see things really close. Their lens is really powerful, okay? But they can't see things then far away. So they can't see things far away. It's because their lens was too powerful. The lens refracts those rays of light way before it hits that retina, way before that fovea. So that's why we can't see things really blurry then. So what I need something then, because this is too powerful, I need something that makes these light rays more spread out. So what we can do is we can put a diverging lens in front of it. So that's what your glasses will be. They'll have diverging lenses. And rather than draw that all the time, what I can say is a diverging lens, we can just draw it with a line with the 2 arrows pointing in. We're trying to show you it's like skinnier in the middle. Okay, so what diverging lenses do is that we have rays of light coming in parallel to the principal axis. They cause them to diverge. They cause them to spread away. So here what's going to happen is when I have my diverging lens, my rays of light come parallel, they're going to get spread out. They're going to hit the cornea, then they're going to get refracted in the cornea. That's most refraction occur. And then the lens is going to cause them to get focused on the fovea so I can see the object. So that means I can see light rays from really far away clearly. Okay. So you also need to know how to draw these ray diagrams. So what I can do for a diverging lens, draw my principal axis, draw my diverging lens, and then how you do it is, let's imagine there's the focal length, so that focal point. Let's imagine we have an object that's here. So there's my object. The first ray of light, you always draw parallel to the principal axis. Okay, so parallel to the principal axis. And then it looks like it came from the focal point. So there's the focal point. It looks like it came from the focal point. So there's my real ray of light being diverged away. And then I'll have that dotted line going back to the focal point, so I knew what angle to draw it. So it looks like it came from there. And then the other ray of light just goes through the center of the lens. And then wherever they cross, that's where your image is. So you can see right there is where my image is going to be. So here is my image, okay? You can see my image is much smaller. You see it's been diminished. And we can see that it's not a real image. So what we call that is a virtual image. So it's a virtual image because it wasn't formed by 2 rays of light actually meeting. So what we know then, remember, power is equal to 1 over the focal point. We can also say power is equal to 1 over u plus 1 over phi. So u is my object distance. So u is the object distance between where my object was and my lens. V is where your image is formed. And V is normally on this side. Okay, think about our convex lens. Let's say our object was over here. There would be V where our image is formed. But because the image is formed on the same side of the lens, V is going to be negative. So the power of all diverging lenses is only going to be negative numbers. Okay, so that's how you know if a diverging lens has been used, because the power will be negative numbers. Okay, the other defect division is called hypermetropia. Okay, so it's the opposite. So hypermetropia means that you are long-sighted. Okay, so hypermetropia means that you are long-sighted. So that means we can see things that are really far away. Okay, so I can see things that are really far away, those parallel light rays, but I can't see things close up. We can't see things close up because our lens isn't powerful enough. So what happens then, if I have light rays from things that are coming close up, my lens isn't powerful enough, so they don't get focused on the retina, they get focused somewhere way behind the retina. So because my lens is not powerful enough, I need to put something in front of it that's going to help me focus, help me refract, help me converge those light rays. So I'm going to put another convex lens in front of there. Okay, so what my convex lens does was, so again, I've got my rays of light from my close object. My convex lens is going to refract them first before they hit my cornea. Then my cornea is going to refract them more. So even though my lens is really weak, it can refract them onto the back of my eye. Okay, so hypermetropia, your glasses are going to have convex lenses in them. So remember, your convex, again, is those converging lens, the one that we can draw with this arrow pointing outwards, so it looks like it's fatter in the middle. Okay, next thing I want to talk about is calculating the power. So we know, we just said, to calculate the power of a lens, we can do 1 over the focal length, which is equal to 1 over u, our object distance, plus 1 over v, our image distance. Sometimes you'll get asked to calculate the power of the correcting lens. Okay? And again, because converging lens forms real images over here, the power of converging lenses is always going to be positive numbers. Like we said, the power of diverging lenses is always negative numbers. So what happens is, let's say someone's got hypermetropia. They're long-sighted. They can see things really far away, but they can't see things close up. So let's say their near point is 50 centimeters, right? So that's the closest they can see things. But we know that the near point of human eye, a healthy eye, should be the 25 centimeters. So what if an object is placed at 25 centimeters, 25 times 10 to the power negative 2? We want the image then is always get formed at the uncorrected point. Because it's not going to be real light rays, it's always going to be negative numbers. So then what the image is going to form at that person's actual near your point. Okay, so that's going to be negative 50 times 10 to the power negative 2. Again, negative because it's in image form there. It's not actually where the object is. So then we could do 1 over 25 times 10 to the power negative 2 plus 1 over negative 50 times 10 to the negative 2 to figure out what the power is of that correcting lens needed to fix the hypermetropia. If, again, we were doing it for our divergent lens, so again, my power equation is 1 over u plus 1 over v. Again, if they've got myopia, it means they're short-sighted. They can see things really close up. They can't see things far away. So let's say this person's far point is maybe 7 meters, right? That's the furthest they can see. So if an object is actually at infinity, that's the far point of a normal or healthy eye. That means we want the image then to get formed at whatever their far point is. And again, because it's an image getting formed there, it's the negative 7. It's not where the object actually is. So 1 over infinity is 0. So the power of this divergent lens becomes 1 over negative 7. So that's why you can see that the power has always come out of those negative numbers. Okay. Okay, last one you need to know about is called astigmatism. And I probably pronounced that terribly, but this is the correct spelling. So what you need to know is the problem with this is that your cornea is not going to be spherical. So your cornea is going to have like different angles of curvature on it. And what that means is instead of your light getting focused nicely onto your fovea, different planes will get focused at different points, right? So you basically get a blurry image. And what all you need to know is that you need to know that it gets corrected by using cylindrical, sorry, I had to stop speaking so I can spell it, cylindrical lenses, okay? You need to be able to read a prescription for a cylindrical lens. So let's say this is the prescription we get for someone from the optician. Okay, the first number always tells you about the spherical lens. So that tells us whether the person's got myopia or whether they've got hypermetropia. Just check my spelling, metropia. The second one tells us about the astigmatism. So basically it tells us how bad it is, right? The power we need there. And this one tells us about our axis of orientation, right? It basically tells us like what axis, how much it needs to be tilted by. But it's always going to be a number between 0 and 180, right? Because if you go beyond, if you switch from 0 to 180, if you go beyond it, you're just flipping it in the other direction, right? So they only can be numbers between 0 and 180. It's not going to go up to 360, okay? So this one about our axis of orientation, you just need to know that it's called the axis of orientation, and it always goes from 0 to 180. Again, this number, we just said it tells us about the spherical lens. So it tells us about myopia or hypermetropia. So again, if I can see the power is a positive number, you should be thinking, what does that mean they have? If the power is a positive number, that must mean, remember, we said they're using a converging lens. So if they're using a converging lens, we know that means that they have hypermetropia. They are long-sighted, right? So that's what that tells us, whether someone's long-sighted or short-sighted. This one, again, just tells us about the power needed to correct the astigmatism, and that's all you need to know for that number. So hopefully this video is helpful, and please check out our previous video on the structures of the eye if you need extra work on that.